Okay, so let me start my lecture today. So today, there's a lot to discuss about dark matter. So I don't know where to start from. So until now, we have been discussing about something known, but we are going to discuss something unknown. But we know that it exists from indirect measurement, which is so this unknown, and we call unknown known. We know it exists, so known, but it's unknown. The precise, property of dark matter, we don't know. So the dark matter evidences for dark matter is from everywhere. So let me first start from the early hint for dark matter. Fritz Zwicky in 1933 coma cluster. So from there, he measured the dispersion of the velocities to infer the total mass of the coma cluster. So total mass will be according to the video theorem. So this is the cluster mass and cluster radius. So this is the according to the video theorem. If you from there, actually this dispersion, the velocity dispersion, even though the coma clusters, you have a lot of galaxies. So here at that time, I think that we have more precise measurement of the same coma cluster, but at the time the number of galaxies is about 100, and each galaxies at the time the called absolute luminosities. Astronomy, people used luminosity instead of mass. So, but the luminosity is the mass for us, the luminosity for galaxy. So it's the absolute, it's the averaged galaxies. So averaged luminosity L equal to, at the time, 8.5 times 10 to the 7 solar mass. So this is sun mass. So this luminosity, so luminous mass. So this is luminous visible, called the visible mass. And also and this is the one parameter, and the total mass is the M cluster. We don't know, but you can if there is no dark matter, luminous mass, L is just the total mass if there is no dark matter. But what this visual theorem tells us is that if you measure this velocity dispersion, just to measure the velocity of each galaxy in the coma cluster, and take the square of the velocity and average them to get the velocity dispersion. And we know that the angular size of the coma cluster, and we know the distance. So this is the coma cluster. So with angular scale, so zeta, and distance to the coma cluster is we call it the luminous distance, and the radius is this is the radius of the coma cluster, roughly twice the diameter. This twice it is the radius of the cluster is just given by angle times the luminous distance. So then we can infer just from the measurement of the distance and the angular size, we can determine the radius of the cluster. And then at the time, the radius, cluster radius was like 2 million light years. So 1 light year, we use the 1 parsec to measure the distance in the astronomical units. So 1 parsec, this is parsec. Parsec, what is the spelling? Parsec is correct. Parsec equal to 3.26 light year. And this is about 3 times something, but roughly 10 to the 18 centimeters, or 3 times 10 to the 16 meter. So yeah, so now 1 parsec is also the reason to use this unit parsec is I think as I remember, there's some sun and earth, and then how do you call this? Parallax. So if you want to see if we want to measure the distance to the stars, there's a sun and Earth. Earth is rotating around the sun, and then this is AU, right? This is AU, the astronomical unit, distance between the sun and the Earth. And this angle is is 1 in 3,600 degree. So this is we call arc second. So this is a arc second. And if you know, we know the astronomical unit, and this, if angle is the arc second, then the distance between solar system to the star would be 1 parsec. So that's how you can define the distance for astronomy. So just to keep in mind that distance and actually maybe 1 parsec. I think I don't remember precise number. Sounds like solar. I mean, there's some Centauri, right? Centauri, the closest star to the solar system is about few parsec from us. So you see solar system like an object, it's about a few parsec. And clusters, actually galaxy, I mean about the galaxy size. Our galaxy, for instance, Milky Way, is about 100 kiloparsec, and cluster is about megaparsec. The radius of the cluster. So cluster is the galaxy cluster. Sorry, it's not galaxy cluster. Galaxies. So galaxies is about, in our case, Milky Way, 100 kiloparsec, and the cluster is about megaparsec. So this also, I think, the Coma cluster is one of the clusters, galaxy clusters. So about million. So light year means in terms of parsec, million parsec, megaparsec. So this is the radius, and we know the velocity dispersion. So at that time, the velocity dispersion, V square, measured to be this value, 700 kilometer per second square from 1,000 galaxies. So then we have input parameters. So this one and the radius. Therefore, they can solve this equation to get the cluster mass. So the cluster mass, therefore, cluster mass, let me go back, 3G, 5 cluster radius times velocity dispersion. Okay, so then the Newton constant. We have to know the Newton constant. G is the Newton constant, which is given by 6.67 times 10 to the minus 11 cubic meters inverse kilogram inverse second square. So if you put those numbers in, then you can obtain about 10 to the 14 solar mass, and 1 solar mass in kilogram is twice 10 to the 30 kilogram. So you can use it to obtain this total cluster mass. But this is the this result, the Beer theorem, is for spherical symmetry when the cluster has a spherical symmetry, the energy, the matter density distributed in a spherical, in a way with a spherical symmetry, then you can get this result. But if you break the spherical symmetry, then this result is more stringent. So you break according to the observation, the coma cluster is not spherically symmetric. Probably, let me show you some figures. Maybe you may have looked for the coma cluster from the Wikipedia. So in Korean, 머리털 자리, coma, comb is the something like 머리털 is the hair, hair 자리, hair cluster. So you can see, yeah, something like this one. It doesn't look like, it doesn't look spherically symmetric. So this one, so some visible stars, some coma cluster. You can take a look. There's some information. So if there is no spectral symmetry, actually, the Beurier theorem plus Beurier theorem. Beurier theorem tells you only this one, twice averaged kinetic energy equal to averaged potential energy minus averaged potential energy, and then actually the Zwicky could take this upper limit on the negative potential energy. So if, but I didn't tell you that if there's a spherical symmetry, gravitational self-energy with the radius r given by sorry, this is m square. Sorry, minus 9. So you can compute the gravitational self-energy for mass distribution with the spherical symmetry and the mass distribution with the radius r, and you can compute the self-energy, gravitational self-energy. And then if you, the previous formula for the velocity dispersion comes from this assumption, the spherical symmetry. But instead, this is what the Fritsch-Zwicky imposed at the time. So according to this one, we don't know the precise value of the gravitational potential. Just from that, but just by using the Beurier theorem, we can infer the upper bound on the velocity dispersion. So actually, it is interesting. It is fun to take a look at the details of the Fritsch-Zwicky's paper in 1933, and also there's paper 1937. So from there, actually the kinetic energy, the average kinetic energy will be just sum over the galaxy. The sum of the kinetic energy of the individual galaxies. And then we define the averaged dispersion by taking this. So m is the total mass, and then this v square is the averaged dispersion for the galaxies. So from there, you can see that if we take this limit only, then m therefore the cluster mass has a lower limit, which is given by this value. So previously, in the case of spherical symmetry, this was just to with this assumption for the gravitational potential. In that case, total mass just to given by 3 times 3 times 3. Okay. So you can see the coefficient, the difference in the coefficient. There's a 1/5 in this estimation, and there's a 5/3. So in the previous estimation, the cluster mass is larger than this limit. So yeah, if for the same velocity dispersion. So from there, in this case, cluster mass should be greater than certain value, which is it's about 1 order of magnitude smaller than the previous estimation. So previously, we had this solar mass 10 to the 14 solar. I'm sorry, this is I just already divided by 1,000. So this is the total mass, and then so we are comparing galaxy by galaxy. So galaxy by galaxy, what is the amount of dark matter in each galaxy? So this M, actually cluster mass, contains luminous mass as well. Luminous plus dark matter. So dark matter per galaxies, just divide by number of galaxies. So we said there are thousands of galaxies in this coma cluster. So therefore, just we are going to use the lower limit. So at least we don't know precise number, but maybe because most of them invisible, we don't know. Just we are inferring. We don't know the structure. I think maybe there's more development. Also, the numbers I'm using like about 90 years ago, right? So it's a long time ago. So this is the total mass, and the luminous mass, as I said before, was just the stars. If you count stars only. Oh, sorry, 7. Let me call this M bar. So therefore, we called mass 2 luminosity ratio about 500. So that means we cannot explain total mass just by the visible mass only. So there is a lot of dark matter in this coma cluster. But the reality, actually, more precisely 530. But the thing is that the things that changed. At the time, actually, the cubic key used, at the time, Hubble found that the universe is expanding, right? Expanding. He found that the universe is expanding, and actually, in order to determine the distance to the coma cluster, you are observing atomic lines, and then the red shift, called the red shift of the atomic lines. So because of this observation, I think the red shift from there, you can determine the distance to coma cluster. So you know the Hubble law, right? Hubble law tells you that the recession distance, recession velocity, that in this case, coma cluster is getting away from us with a certain distance, v, and the Hubble constant times luminosity distance. So this H0 is the Hubble constant. So this v is the recession velocity. So you know the Doppler effect, the Doppler shift. The red shift is the Doppler, kind of Doppler shift. You can measure the velocity, and then this L, the distance you can measure from the luminous mass, luminosity. Of course, in order to determine, you need to know the absolute luminosity. It's absolute luminosity. So we need the, I think it's so complicated. In any case, the distance, you can measure the number of photons and flux, I mean, the photon flux, and then you can measure the distance. Then this is how you determine the Hubble constant. Oops. So you have two different informations. So atomic lines and the photon counting, and the Doppler shift is the line shift. So, but the Hubble determined the Hubble constant to be I think that you may know this story well. He was very, how to say this, the plot is not linear. So if you see the v or redshift equal g, that the redshift as a function of distance, kind of the data, galaxy data is randomly distributed, and then you just draw linear line to fit the data. And this is how he got this H0. But currently we know that the really the Hubble constant equal to about 67. There is more precise, but Hubble constant is measured to be 10 times smaller than H0. And then there was a lot of problem if you take this large Hubble constant. The age of universe is problem. So age of universe is inversely proportional to the Hubble. So 10 times smaller, 10 times smaller. So just 1 billion. 1 billion years, but the reality from this true Hubble constant, the lifetime, the universe lifetime. It's about its lifetime. I mean the age of the universe. Sorry, the universe will live forever, but the age of universe is the currently 13.8 billion years. So this smaller age of universe was problematic for many reasons. So galaxies, galaxy clusters older than this estimation. So at that time, the scenario of expanding universe made some problem, but now it is okay, no problem. So I think the reason that I'm talking about this is that let me go back to the Hubble law. So now the Hubble constant, actually the Zwicky used this value, wrong value for the Hubble constant to get to infer the recession velocity. So if H0 is smaller, then luminous distance is larger. Because of that, as I said, the cluster radius equal to angle times luminous distance, and then they measure the angular size of the coma cluster. So theta is fixed, but what matters is the distance to the coma cluster, and the distance gets larger by factor of 10. So because of that, the radius of coma cluster now is bigger. It's 10 times bigger. It's about this size. So because of that, there's a correction factors here and there, and so what would and also I actually from this discussion, I think if you apply the Beria theorem, then here the lower limit on the total mass is proportional to the cluster radius. So cluster radius is 10 times larger now. So you would guess the luminous mass is larger by 10 times larger. But and also this luminous mass is not correct. So because of that, we thought that dark matter is much more abundant, but this is not true. So the real value is okay, let me give you more precise value. The lower limit is now this one, and the luminous mass is now so from there actually average the so mass per cluster is now 10 to 11, but the luminous mass they found more stars. Because of that, they did their counting was wrong. So actually, luminous mass is now, it was 10 to the 7, but now 10 to the 10. So because of that, you can see now the ratio, mass to the luminosity ratio, called mass to luminosity ratio, is now about 12 with 10 something. So because of that, about 90% of the total mass is invisible. Okay, previously mass to luminosity ratio is like 500. Now we reduce it down 10, about 10. So, okay, so this is the first hint. And there are a lot of hints from rotational, galaxy rotational curves. So this is the first story for dark matter that you are familiar with, and also the galaxy rotation curves. Do you have any question?
How to say? I wonder how they could found the new unobserved, previously unobserved luminosity. Then I am free.
I don't know.
I wonder.
I look at the dictionary. So the current value for the luminosity,
I'm sorry.
luminous mass.
I meant how we could find the previously unobserved luminosity mass, and if there's something room for we could found more luminosity than for future.
I think mostly I think that at the time there was no X-ray searches, so we are observing photons, but if I mean they are observing photons by naked eye, right? So the visible light. So if you go outside the window of the visible light, you don't have access by naked eye. So I think that you can also estimate X-ray mass. So if the photons coming from the coma cluster in the form of X-rays, you don't have, they didn't know how to observe it. So now we have a lot of development on the X-ray observation, X-ray telescopes, like not only optical, so called the optical telescope and the X-ray telescopes. So probably, but I didn't look at the details. Maybe it'll be nice to look at the details. What makes such a big difference in the luminousness? Yeah, but I found that the X-ray search is also, there's a map from the X-ray. You can map out the shape of the coma cluster just from the X-ray, and then they see there's the core and then something like that, distribution, something like that. So maybe, yeah, because of that, but I don't know the details. But I didn't actually, when you look at the textbook, normally what you can see is the very old estimation by Fritz-Zwicky. So mass to luminous ratio is about 500. It's too much. But you know that the dark matter is not that abundant. I think that now we are converging to kind of consensus. I think the dark matter is there, but that's about 90%, something like that. And also, yeah, let me go on to discuss. I mean, in the cosmological scale, document is about 80%, 90%. I think that is kind of, there's some environmental effect, so maybe the precise value, precise document abundance may depend on the environment. So, okay, so the galaxy rotational curves. So it's like rotating around the sun, right? But we know that there's a center of the Milky Way galaxy, and the sun is moving around. This is this Milky Way center, galactic center, moving around them. So not only sun, but also there are many other stars out there in our galaxy. So we can measure in the rotational curves, not only ours, but also I think in our case, there are, in our case, the first, I think for instance, fourth, Lubin, Bella Lubin is the famous for this one. Female astrophysicist, Bella Lubin, and fourth, 1970. Optical observation of M31. So this is Andromeda. Andromeda galaxy and rotation. As you remember, according to the Newton's Newtonian mechanics, Newtonian gravity, gravitational force. So if you have a test mass, in our case, our solar system. So maybe I'll replace this R. So this is R. Distance from the center of the galaxy. And Newtonian force so circular motion, let's say the solar system undergoes circular motion, then this right-hand side is m times acceleration. On the left-hand side is the gravity force. From there, so m is in our case, the solar mass, sun's mass, the V equal to, and m is the mass enclosed to within radius r. So the total mass cannot be concentrated at the origin. It can be distributed, but we are assuming spherical symmetry. So then you get this result. So V is the velocity, rotational velocity, right? The V is here, right? So because of that, as you know very well, rotational curve, decreases by 1 over square root of r, so decreases. But this M is total mass. But if you go inside, you have a mass inside. I mean, the mass, if you go to the inner region, then because of the mass inside and outside, so the velocity curve will be something like this one. So like a disk. In our galaxy, we have a disk. Something like that. Concentrated on a certain region. Then if you go outside disk, there's nothing, almost nothing. Because of that, you can think of total mass concentrated at the origin. So you will expect this kind of thing, right? But according to the observation, including I think the 1970 Rubin and Ford, they observed the rotational curve of the Andromeda galaxy, and then they extended I think the 10 galaxies. 1978. So they have more data, and then what they observed is this kind of tendency in the velocity curve. The velocity does not drop as you go to the larger distances. So therefore, the total mass keeps increasing instead of being localized on the disk. So therefore, the velocity curve becomes saturated. Because of that, the M, a function of the radial distance, should be proportional to radius. And we know that the total mass is integral, the volume integral of the matter energy density. Then we can infer the radial dependence of the matter density. So this is the proportional to R. So this one must be 1 over R square. In order to cancel this R square. So therefore, there's an unknown form of matter with this profile. So dark matter peaked at the center of the galaxy. Just by simple reasoning. But the reality, actually matter density doesn't increase. It becomes singular, right? The density, dark matter density, is singular at the origin, according to this formula. But the reality is not true. If you fit to the galaxy rotational curves inner region. So normally we took isothermal profile. Just modifying simple modification of this dark matter profile, some phenomenological modification. you can try to fit the galaxy rotational curves by taking this kind of ansatz. So this R here, R as the core radius. And also, in other words, the dark matter profile we call the halo profile, because it's like a halo spread over into the bulk region. So it's not this dark matter is not concentrated on the disk, so it is spread over into the bulk region. So it's the halo. So it's a halo, dark matter halo. It's like a moon halo. Then you see the moon in the if you see the full moon, then you see there's some kind of cloud around there. Spread the moon night is spread over into the bulk region beyond the boundary of the moon. So and the RS is the core radius, and the rho s the core density. Then if you draw density, dark matter density as a function of radius, and previously it will be something like this one, right? It's peaky and it becomes divergent as you go to the inner region, but now it's smooth out because if you take R to 0, then the density becomes constant. So core, this is a core density, and this is you can see the deviation from naive expectation by the 1 over R square at the core radius. So then you can, maybe most of dark matter is concentrated within the core radius. This is how you define the core radius. But this is not the only, dark matter profile. So because as I said, this is the phenomenological, right? So isothermal maybe might imply kind of constant temperature. This is called isothermal, thermal equilibrium. And so it's like isothermal means if you can maintain the temperature as you move along to the radial distance, for instance. So phenomenological due to the fact that there's a 1 in the denominator. If you don't have a 1, it is precisely isothermal. So you have some cutoff in the short distance. And then there's another interesting profile, is the Navarro Frank White. So before going to this one, so R is much smaller than the core radius. As I said, the dark matter density becomes constant. So we call this is core. Okay, and the Navarro Frank White profile is also from phenomenological. So in this case, there are 2 fitting parameters. Here, the isothermal profile, there's a rho s and rs, right? Similarly, NFW profile, there's you have a tendency. So for small radius, it is divergent, but it's a cos p, but less cos p than the previous estimation. And if you go to larger distances, the density drops faster than the previous estimation. So 1 over r cubed. So this is the NFW profile. But let me, because there are some problems at small scales in galaxies, so let me just focus on quad versus cos p profiles. Core cos p profiles. So in the case of core, so kind of isothermal. So inner region, dark matter density is almost constant. Then total mass within the radius is proportional to the volume factor, right? Volume times the constant density. Therefore, the rotational velocity is linearly increasing. This is how you can see, you can measure the tendency of the rotational velocity in the inner region and to fit your model to the data in the core case. And then cos p, let me take the cos p. I think that this is the NFW profile is favored because of the dark matter Inbody stimulation. I forgot to say. So this is the Inbody stimulation is dark matter only stimulation. And you put number of dark matter particles and then just impose gravity only between dark matter particles and then see how they evolve in time. The Inbody stimulation, I think the NFW profile is more consistent with the Inbody stimulation. So then in the inner region, becomes cos p, right? It's not isothermal, but it's a cos p. Then you see there's the 1 over r dependence. Then the total mass will be integral of r, which is r square. Therefore, velocity curve, you remember velocity was m gm over r over 5. I'm using this one. So if we plug r square there, then you have a square root 2 velocity. So quad 1 and cos p 2. Quad 1 cos p. So the dark matter density behaves like something like that. And you can infer the velocity curve in the inner region. So I don't know how to draw this. Oops. Maybe it should be. Maybe I need to use a different notation. Okay, so this is the I don't know, slope. So it looks almost the same. So maybe I need to change this. In any case, this one, in the case of chord profile one, the velocity increases faster than the one in the cos P profile. So then the velocity, you have a larger velocity in the inner region, okay? Maybe before we make a pause, let me give you another profile. So this is the fit well at a small scale. Anasto profile. Yeah, a little bit complicated expansion, but it is that this ionosphere profile fit well at small scales. This is how. So there are representative dark matter profiles. So isothermal, NFW, ionosphere profiles. So there are all phenomenological. Normally, NFW profile kind of indirect detection in order to determine the indirect signal for dark matter. You need to know the dark matter profile because the dark matter distributed kind of all the way toward the galaxy center. So galaxy center, dark matter peaked at the galaxy center, but you also have dark matter all the way to us. So you need to integrate over the dark matter signal from the galaxy center all the way to us. Because of that, dark matter indirect signal depends on the dark matter profile. So, but normally NFW profile, people use the NFW profile. And I think that I have a few things to discuss. But, let me stop for a moment and I will come back 11:20, okay? Do you have any question? No? Okay. So see you in 10 minutes. Recording. So dwarf spheroidal galaxy, let me show the slide from the beginning because I forgot to recording. So local dark matter density. Okay, so two measurement, local and global. And now we are going to discuss dark matter velocity distribution. And for dwarf spheroidal galaxies, so it's a satellite galaxy, you know, belonging to our galaxy, small size dwarf galaxy. It is small, so because of that, the number of stars are small, so 10 to the 8 solar mass, and halo size also small, about 10 kiloparsec. So from there, dispersion is about 10 kilometer per second. And for galaxy cluster, as we discussed for coma cluster, halo mass is about 10 to the 15 solar mass. Because typically this is one galaxy 10 to the 12 stars, and one galaxy cluster is about 1,000 galaxies. The 1,000 galaxies, each galaxy contains 10 to the 12 stars, so 10 to 15 is the rough estimation for galaxy clusters, galaxy cluster mass. And halo the radius is 1 megaparsec. So from there, dispersion is about 100,000 kilometers per second. So velocity, dark matter velocity change depending on where dark matter reside. So dark matter could be, so this is the velocity dispersion. You see 10 kilometer per second, about 100 meter per second, and 1,000 kilometer per second. So this is dwarf and the Milky Way galaxy, and also galaxy cluster. So in principle, we cannot produce dark matter particle. I don't know. You can produce in principle at the colliders, but here, so we call this kind of cosmological colliders. So dark matter velocities vary from small velocity to large velocities. So in principle, you can test dark matter interaction depending on the velocities. Okay. I don't know if I can. So now, for the rest of minutes, I will. Sorry. Yeah, the reason that I'm talking about this is because there is confusion on the dark matter distribution. So if dark matter is in thermal equilibrium, certainly dark matter must follow Maxwell-Boltzmann distribution or some quantum distributions, depending on the spin of dark matter. Fermi-Dirac or Bose-Einstein distributions. But even if dark matter dark matter is not in thermal equilibrium, if you have a sufficiently large number of dark matter particles, you can infer what the distribution of dark matter is. So this subject that I'm talking about is just based on the statistics. So all the point in the phase space, all the points in the phase space are equally probable. So that's what, as far as the energy conservation or angular momentum conservation is guaranteed, you can be anywhere in the phase space. So this is what we can say for a system with many particles. We cannot describe the motion of individual particle. You cannot keep track of individual particle because there are too many. So that's why we are going to discuss a phase space distribution. So let me give you one example, maybe, and then So I think that you have already taken some classes on statistical mechanics, so I don't have to repeat them here. Just the phase space distribution is a general function of position and velocity and time. This is the describing number of states in this position and velocity space. So sometimes instead of velocity, people are using momentum instead of velocity because for massless particle, there's no meaning for velocity. So velocity is always speed of light. So it's more appropriate to describe phase space in momentum space instead of velocity. And also, according to the quantum mechanics, you know, there's a relation between x position and momentum. And so here, this F is the density, number of states. And so this F we call phase space distribution. And this is the engine, is the function of constants of motion. As I said, every point in the phase space is equally probable as far as the momentum or angular momentum are conserved. So that's why I'm saying that this phase space is a function of constant of motion, like energy and angular momentum. So, for instance, the phase space is a function of total energy. So as you remember, in the case of harmonic oscillator, you know, x dot 1D harmonic oscillator, you can draw ellipse in this phase space, two-dimensional phase space. And sorry for drawing is supposed to be ellipse. And you can be anywhere along the ellipse as far as the energy is conserved. So this contour is a contour along which the energy remains constant. So if you increase energy, then you can increase velocity as well as position. So then you can draw another ellipse as you increase energy, right? So because of that, there is a dependence of the phase space distribution on the energy. So I think in terms of for instance, I think you can define the density stuff. It depends on, the phase space depends on the coordinate. So if you choose the radial coordinate, you can see some dependency, for instance. So this is just the definition of the phase space distribution. And now, because of this, we are going to consider a system of many particles. So instead of defining the total energy, let me define the energy per tested particle mass. So you can add one more particle in the system, and then how does this particle behave in the presence of many particles. So then we define this curl E, that is the potential energy plus, I mean, the negative, there's overall negative sign, but so this V psi equal to minus phi is the gravitational potential and divided by particle mass. So, and then there's minus sign here. So the opposite, the gravitational. So this is the gravitational potential. But I don't know, but this is how people define. So from there, the phase space distribution is function of curl E, and this curl E depends on this kind of total energy for test particle mass. This in this form, exponential e to the curl E divided by sigma square, and the sigma is the velocity dispersion. So this velocity dispersion is not determined by theory. It must be determined by observation. So you can say this sigma is the arbitrary parameter in this case. So from there you can infer what is the energy, average mass density. So average mass density is an integral of the velocity this integral is the exponential divided potential divided by V square over 2 over dispersion. So again, this density depends on not only velocity dispersion, but also gravitational potential energy psi. And the gravitational potential energy can be factorized. Therefore, averaged mass density depends on the gravitational potential. So I think that this capital psi is a function of r, radial distance. So you can infer the local mass density from the gravitational potential. So actually, this is the local, as I said before, the local, in the case of local measurement, there's one-to-one correspondence between energy density, local energy density, and gravitational potential energy. So gravitational potential energy. So here, another implication. So now we know that there's one-to-one correspondence between dark matter mass density and gravitational potential. Then we can determine the dark matter profile with that information. So let me call, there's a proportionality constant for the density. Okay, so there's a sigma c, rho c is a constant. And here the psi is a gravitational potential minus gravitational potential. So that satisfies this Poisson equation. So rho is the energy density, and then the gravitational potential is determined and responds to the energy density. so locally determined, right? So, and then just we have a relation here between rho and psi. So we are going to use this Poisson equation. So for spherical symmetry, psi and rho, they are function of R only. Therefore, the this Normalization operator can be written down in the radial coordinate only. Therefore, the Poisson equation can be written in this simple form. Sorry, this is the so this is the Poisson equation, and then we plug instead of psi, so psi from this equation, so psi equal to sigma square and log of rho over c. So the derivative of the gravitational potential equal to, so sigma square is constant and rho c is also constant. Therefore, 1 over rho d. So we get this, right? So then from this equation, instead of psi, now we are replacing psi by rho. Then sigma square. Okay. I multiplied r square on both sides already, so we have this. So then you can look for the solution to this equation, and maybe you can look for the polynomial solution. So then you see d rho over d r is proportional to r to the, sorry, r to the n minus 1. Something like that, right? So that means, therefore, left-hand side is the, so this combined, these two combined to be inverse, right? So this is r. This is the r square. So left-hand side is independent of n. The right-hand side, we have n dependence. So because of that, this is just constant. Left-hand side is constant. So n is determined to be a -2. Right? So then therefore, energy density is a constant c over r square. And then you see c is not arbitrary, okay? Because the from this equation, we have some constant on the left-hand side, some constant on the right-hand side. So if you do the matching correctly on both sides, then the c equal to sigma square over 2 pi g. Therefore, you can conclude that you get this kind of profile. So the energy density is proportional, inversely proportional to R scale. We call this is the isothermal profile. So we have in the case of system with many particles, we are ignoring the interactions between the particles, or they are weakly interacting. It's like an ideal gas system. So we are ignoring collisions between particles. So if you have a collisions between particles, the story changes. So distribution will differ from this isothermal distribution. And if you have a core, maybe then, I mean, this, as I said, the isothermal profile, I discussed isothermal profile, but it's not exactly the same form as this one. Before we have isothermal to rho S. It becomes isothermal when R is much greater than the core radius. But it is not it's only in the certain region, only for the large radius. So because of that, maybe you can kind of infer the product of the core radius scale and core mass density in comparison to the isothermal profile as discussed before. So another implication. So this is the implication for dark matter density according to the phase space distribution. And another implication is for dark matter velocity distribution. So phase space distribution, as I said, is proportional to curl E over sigma square. And this is the to the psi minus 1/2 sigma V square or sigma square. And then this psi is a R dependent quantity, right? It depends on the position of the dark matter particle. In this case, the distance from the center of the galaxy. And so you can see only a velocity dependent part. It's like even if you make a gas in thermal you can keep the gas in thermal equilibrium, and in the atmosphere, you still have dependence on the height. I mean, you have a dependence of the gas density on the height above the surface. Yeah, in any case. So from there, phase space distribution is the like this one. But of course, you can ask a question in the first place: how we determine how determine the form of the, not this one, sorry. How do we know about this dependence? How does energy depend on, how does the phase space distribution depend on energy in this particular form? How do we know? You can ask such a question. So this is from the Liouville equation in gravity. I think the Liouville equation applies in the presence of any type of forces. So, but in particular for gravitational force, you can still apply the Liouville equation, Liouville theorem. I think you can refer chapter 7 in Marion. You can find this. Then you can see this is what it is. Okay. So there's no doubt on the dependence, energy dependence. Certainly, according to the statistical mechanics, you only have to count number of possibilities and something like that, and then you will see the same result. But in particular for the dependence, I think that for velocity dependence, there is no, you don't need the Liouville equation to determine the velocity dependence, but the dependence on the gravitational potential, you need the Liouville equation. So I think that you have learned that already, so let me go on. So we know that this is the velocity dependence, but we don't know what the sigma is. And in the end, if you take the velocity square, and then if you take the average of velocity square, then that is because there is no normalization factor yet. So we need to divide by normalization factor dv, v square, f of v, and 0 dv square, f of v, and v square. So we have another v square because we are averaging over it. So in conclusion, I think that you can show that these integrals can be written as a ratio of the gamma function. And this is the 3 times sigma square. So therefore, sigma square equal to 1/3 of the velocity dispersion. So if you measure the velocity dispersion, then you can determine sigma in this case. And because there's the factor 3, because we are in 3 dimension. So if we are in 1 dimension, we don't have a 3. So because of that, we can say that sigma is the 1-dimensional velocity dispersion. And then we have a 3 because we are averaging over a 3 dimension in this sense. So then we can also determine the normalization factor. And now we can replace it by dispersion, or we can introduce V naught square instead of dispersion. Then we can determine this overall constant normalization factor from the integral. So here, actually, we need to take the volume integral, including the phase. So, including the solid angle integral. So we need to take this normalization. for the phase space function, then you can determine C equal to this way. Therefore, okay, so this one equal to so according to the real bell theorem, you have determined the dark matter profile, the radial distance dependence, and also velocity dependence at the same time. It's very interesting, but here the V0 you can think of maybe in comparison the Maxwell-Boltzmann distribution with the temperature. You see the phase space distribution is proportional to e to the E over KT. So E for, if you ignore the interaction, then you have kinetic energy. So in this case, you can write also Maxwell-Boltzmann distribution in this type, and the V0 still can be identified. In this form. So this V0 square is related to the dispersion, right? So dispersion in this form. So 2, something like that. And maybe you can cancel this one. So this is the usual thermal average equipartition theorem in thermodynamics. The kinetic energy, average of kinetic energy is written in terms of the temperature, right? But this is in the case of thermal equilibrium, in equilibrium. So this parameter V0 doesn't have to be related to temperature in our case, because we have a kind of dilute gas, and they are not interacting with one another, and just they are distributing randomly, but we don't know the motion of individual particle. So just according to the statistical mechanics, we can just infer that maybe individual dark matter particle must follow this distribution. And the another point is that, of course, the velocity, dark matter velocity in this case can be from 0 to infinity, right? But in the case of large velocity, you have an exponential suppression. But in reality, we have escape velocity. So if dark matter velocity is too large, then dark matter cannot be bounded to the galaxy, right? So because of that, you can say that the escape velocity can be determined standard way. In this case, test mass m and the halo mass at the position of the halo radius, that is the maximum distance in the halo, the energy vanishes. Then if velocity is greater than, total energy is greater than this, zero, then it will escape. So, so therefore, velocity, so this is the way. And then the escape velocity is defined this way. Escape velocity equal to in terms of the halo mass and the halo radius. So you can infer that this is the about 10 to the -3, the speed of light. So about 100, so a rough estimation is the 300 kilometers per second. But there's some, I don't know, so it's not precise. So I think let me quote reality. Escape velocity equal to in Milky Way. Milky Way escape velocity is the 544 kilometers per second, and the V0, so dispersion, so V0 the velocity dispersion in Milky Way measured to be 288 kilometers per second. From there, V0 appearing in the phase space distribution can be written in this way, so which is the 235 kilometers per second. So I don't know, actually this one, there's a reference to that, but I didn't look at the details, just this is what I can get from that value. But there's also another value in the literature. So I don't know which one is correct, but I personally, I use this one also in the last project. So 220 kilometers per second. So this V0 is important because in the end, the velocity distribution, we need to draw. So this is the velocity distribution, V square, and the phase space distribution. You see, we have this kind of distribution. The maximum appears at V0, right? So maximum probability is at V0. The V0 is important. So maximum probability, and we have a more chance to detect dark matter at this value, 220 kilometers per second. And then also signal, it depends on the dark matter profile. So we are going to discuss this in more detail. And yeah, when you actually, we need to average. Actually, I forgot to tell you about when we obtained direct, where is the here, direct detection signal, we need to average over velocity. So this which this it means average over velocity. So this V square, in the end, you have known already this Maxwell-Boltzmann distribution. So sigma V equal to this means this is this one. So this average over dark matter velocity. So here, of course, this one, they are all function of v square. So this one just 4 pi v square. This is the So now, since we know what is the form of f, you only have to know what is the velocity dependence, or is there any velocity dependence. But here, the one thing is, and so if infinity, so this infinity must be v escape. So mostly, I mean, for practical purposes, I think that you don't have to cut off, but here, you need to cut off integral. You can keep it like this. I think maybe you have seen this eta something, eta v something. I don't know, eta v. I don't know. Let me introduce zeta function. So the step function, right? This is 0. So minus. So this is the step function zeta equal to 0, 1, 0, right? So step function, sorry, x. So I want to be v equal to v escape. So maybe this one is correct one. So zeta. Then you can account for the dependence on this escape velocity. Okay, so in principle, you can calculate. I mean, so but I kind of error function. It becomes error function normally, but it's not escape velocity can be important, but it makes some small corrections. Do you have any question?
Well, if there any how to say, if there any reason about the sigma v is isotropic under v?
A region.
Yeah, region, or if that's just a function?
Yeah, it's a function of v scale because Galileo transformation. Galileo. So it does not in the we are in the non-relativistic region, so we don't have to impose Lorentz symmetry. So there should be frame independence. So frame independence must be taken into account. So if sigma v is velocity dependent, must be invariant under the Galileo transformation. So if you, I mean, frame independence, if you go to another frame with a constant velocity, you must not see the effect. So and also, yeah, okay, Galileo rotation. So Galileo transformation changes velocity. Yeah, so maybe this v is better to, this v is the relative velocity. If you, because we are considering collision of two particles. maybe it's better to say in this way. So Galileo transformation transform. So this is the frame dependence, right? The capital V. So in the case, this combination difference, this is a relative velocity. It's an invariant. And then this is one type of Galileo transformation. The Galileo transformation also contains rotations. So because of that, velocity should be scalar quantity. So this is also invariant under the rotations. So normally, yeah. So yeah, this is the how we can see the V-square dependence in the cross section sigma wave. Okay, so do you have any more question? So otherwise, I think that we can. This is the end of the lecture.